So, then it's my pleasure to open this workshop. Welcome to all of you. Some of you have traveled from far away, from San Diego, I think from Canada, and Australia is the furthest. This week meets us here in Basel in the hottest week of the year, and it's unusually hot for Europe and for Switzerland also. There's the Rhine, the river in Basel, and many people went swimming already in this river. Last week was the official swimming day where they closed the river for boats traffic, and then thousands of people jump into the river and swim. And there's some area between two of the bridges where you can swim. You can cross this historic bridge swimming, and maybe in your hotels you can borrow one of these swimming bags where you can put your clothes in, and then seal it watertight, and then lean on it and go down the river.
You can also swim upriver.
Yeah. And you should not cross the river because usually, except on this one day, there's boats traveling, so you have to stay close to the edges. But there are some posts, and I think they're probably also in English, that explain where you're allowed to swim. Obviously, you need swimming clothes and pants for that. So this workshop is a 1-week workshop. Yesterday evening we had dinner in the pizzeria. We have sponsoring from the Biozentrum. Erich Nick is the director of the Biozentrum. He will say a few words soon. And also from an NCCR, which is a Swiss Center for Research in membrane protein's role for the membrane protein transporter type in medicine. And this NCCR is called TransCure. That supports our workshop. Then the companies FEI, Electron Microscopy, and TBIPS, they produce detectors, cameras, CCD cameras and CMOS cameras for electron microscopy. We are here in the Pharmazentrum building, which is the partner building from the Biozentrum. The two buildings together host the Biozentrum mostly, which is a center for molecular life sciences. The University of Basel has also other biological departments. One is called the Department for Biomedicine. They are close to hospital applications of biology. And then there is a basic biology department, and then the Biozentrum. And the Biozentrum is focusing on molecules and 5 disciplines. And I would welcome Erich Nick now, the director of our Biozentrum, to tell us a bit more what the Biozentrum is doing. Erich himself, you were also a Max Planck director in Germany. You work on cell cycle and chromosome stability. We have a research lab. Try to get the best scientists to head our Biozentrum. So you were appointed by the faculty members themselves. Please, Erich, stop here. You have your own,
my own
presentation.
Great. Well, thank you very much, Henning, for this introduction. So I'd like to join Henning in welcoming you to Basel and to the Biozentrum in particular. I know that you will visit the China on the last day, so you'll see it's a very impressive operation. A lot of high-tech stuff, but of course you're maybe less impressed than I am by this high-tech stuff. But I want to now give you the broader picture about China being embedded in the Biozentrum, the institute that devotes itself to the understanding of processes in life at the level of molecular biology. Just a few key facts. We are the largest department of the Faculty of Sciences at the University of Basel. We have a budget of about 60 million Swiss francs per year, which is pretty much the same in dollars, maybe $62 million. That money is spread over about 550 people, 30 some research groups. We publish more than 200 papers per year, many in top journals. And then we'll get in hopefully 2017 a new building. The old building is on top and the new building is at the bottom. It's going to be twice the height of the old building. You see still the old building here. This is just a model of the new building. So we very much look forward to that. I'd like to emphasize that as other institutions in Switzerland, the Biocenter is very international. We have, as I said before, about 550 collaborators. They call from all different types of countries. Of course, the majority from Europe, but we have about 50 people from Asia and about 15 people from North America. We pride ourselves, I think, of being very interactive. People collaborate a lot within the house. But for organizational reasons and partly historic reasons, we have what we call focal areas, subdivisions, if you like, where people focus on particular themes. So they are named here: growth and development, infection biology, neurobiology, structural biology and biophysics, and computational and systems biology. I'll just show you. Oops. I get back here, return. Oh. Yeah. I'll just show you a few faces. This is neurobiology. It's about 2, 4, 6 labs. This is constantly changing, people leaving, people coming. This is growth and development, of which I'm myself part, as you see there. You also have junior people, like the person just above me, who is a career development awardee by the Swiss National Science Foundation. Then we have infection biology, a subject, of course, which is very close to clinical applications. Then we have computational systems biology. As you see, all these groups are about 5, 6 PIs, and oftentimes a single PI is actually affiliated with more than one group, so that also helps to foster interactions. And last but not least, structural biology and biophysics, so nanobiology, and Henning Stahlberg is a member of this group. And the whole operation is supported by an increasing number of technology platforms. The Center for Cell Imaging and Nanoanalytics, or CECINA, is by far the largest of these centers, but we have also, jointly with an ETH institute here in Basel, we have next generation sequencing. We have in-house light fluorescence microscopy imaging core facility. We have microarrays and SNP technology and life science training facility. Microscopy Center is actually a traditional institution. It goes back to the time when, transmission electron microscopy and scanning electron microscopy merged. So this is mostly an electron microscopy center. And we have a proteomics core facility, again in the house, a biophysics facility, and a research IT unit. So I think it's fair to say that we are very well set up to do modern research in molecular biology. And I don't want to take up more of your time other than emphasize that I'm very happy that you're here. I'm very happy that Henning organizes such types of courses, because I think they do a lot to foster science, to foster interactions. And so I do hope that you will enjoy your week. In Basel, it should be hot enough, as Henning said. I hope you'll find some time in the evening to go to the Rhine. It's very nice. You'll see Basel offers a great quality of life in addition to excellent science. So have a good time. Okay.
Thank you. Yeah. You're welcome to stay if you want. Well, you might have some other duties to attend to. Okay. So this is about electron microscopy of membrane proteins. Electron crystallography is one of those applications. The focus of this workshop, it's the 4th workshop in this series, will be on image processing mostly. But today we still want to cover the steps before the image processing, which I briefly want to introduce here. So what you need to do to study a membrane protein is an expression system, obviously, to get your proteins. Cell-free expression is the most recent development in this. Obviously, you can get bacterial expression systems or mammalian cells, and they're more expensive and more complicated, but sometimes needed. Cell-free expression is done by several groups. I also heard of groups that try to cell-free express membrane proteins directly into lipids for 3D crystallization or also for 2D crystallization. Then you need to purify the membrane proteins by the common methods. We will not spend time on this in this workshop. We have a detergent Dropbox machine that Andreas Engel invented. I don't know if Bianca is going to speak about that. It's a machine that allows you to measure the concentration of detergent in your purified sample without losing your sample. You put a little bit of the sample that you dilute below the CMC of your detergent on a piece of parafilm, then you measure the contact angle to the parafilm, you take the sample back up and can continue using it for other measurements, and this allows you to determine from the contact angle the detergent concentration in your sample. 2D crystallization is a difficult topic, but I still claim it's easier than 3D crystallization. Priyanka will give a talk about that when I finished here. Priyanka is also the first author on an extensive review that she mostly wrote that appears now in, where's this? Here. In Comprehensive Biophysics. It's a book, and it's, I think, 80-page review, and the book is very expensive. For this workshop, we will make the PDF of this review article available to all of you. It contains, among others, an exhaustive table of all 2D crystal membrane protein research papers that we found, where people 2D crystallized membrane proteins and then got two-dimensional projection maps or 3D structures. And it's about 400 or 500 publications that Priyanka collected with the help of others. And we have summarized which protein it is, what resolution was attained, where is the protein from, how was it expressed, what lipid was used, what detergent was used, how was it crystallized, what buffer conditions, what pH, what temperature, what method, dialysis or biobeads or so, and what is the reference. It's an exhaustive table. There's also other tables in this review, a table about all detergents that you could use, a table about all kinds of lipids. If you want to two-dimensionally crystallize membrane proteins, I would recommend this as a starting point to see what has been tried in the world with membrane proteins. And the proteins are sorted by type, so if you work on a certain porine, for example, you can just go to the porine chapter or porine section and look what porines have been two-dimensionally crystallized and how, and then you find the references who did that. Priyanka has done a lot of work on that and will tell us later more about that. The next thing is sample preparation, and we will not spend time on this in this workshop. Philipp Ringler will show a bit about that. We have, however, experts here in this room. Philipp Ringler himself, Muhammad Shami in the back, Priyanka. Many people here know a lot about sample preparation for 2D crystals, and you can just ask questions to Philipp Ringler. He will give a talk later, or Muhammad and others. Electron microscopy to record pictures of your 2D crystals is done with ever-increasing and bigger and more expensive machines. A lot of hardware improvements has happened in the last years. These things get very expensive now. Currently, Anshif Cheng, for example, from San Diego, works on automation, and he will present something about that. And a lot is happening with beta detectors to replace photographic film, now with direct electron detectors, radiation-hardened CMOS detectors. They're very expensive still, in the order of €500,000 or $500,000, but the price is also expected to come down soon. Many labs have high-end electron microscopes, and I don't know of a single lab that would not welcome you as a guest if you want to use one of these big machines. In San Diego they are, in Frankfurt, and also here in Basel. If you need access to a very high-end machine in Kyoto, in Japan, Fujiyoshi's machine, all of these labs usually welcome you to use the machines to collect data for free and without having to co-author the owners of these machines in general. Image processing was started with the MRC programs by Richard Henderson in the 70s. This is the gold standard still, but it's hard to use, so we have written this 2DX front end for the MRC programs and then added additional functions into the back end also, and we will learn the whole week about this. IPLT is an alternative software package. It was written by Ansgar Philipsen in the lab of Andreas Engel here in Basel at the time. It's a ground-up new development that is not compatible with MRC, but has some functions, and it's interesting, especially for electron diffraction processing. XDP is a Japanese software package. that also is a front end to MRC, and several labs, or a few labs, use XDP, which was written in the lab of Fujiyoshi, for electron diffraction processing mostly. In our lab here in Basel, we focus on single particle extensions of 2D crystal processing. Xiangyang Zheng will tell us more about that, and you will hear about this during the workshop. So the bottlenecks or the frontiers in electron crystallography is you need a good sample. A good sample shows you a narrow, slim gel filtration peak. That shows you that you have one homogeneous population. And if you want to set up a dialysis that crystallizes your sample within a week at room temperature, then your sample needs to be able to survive at room temperature for a week. And so that means the gel filtration profile should still look the same also a week later. That's one thing. For crystallization, this can partly be automated. But many labs don't believe in automation and 2D crystallization. There are different opinions on that. I myself also have that. Grid preparation is still in the development. Data collection needs to be automated. I think in San Diego, the people are the most advanced in this. For image processing, we will hear a lot about this. With 2DX, we focused on throughput, on automation and user-friendliness, and we are working on single particle extensions. In Karolinska Institute, there's also Philip Köck advancing methods in that direction. And we have a solution for filling data into the missing cone, which we will also hear about this later. X-ray crystallography for membrane protein structure determination is super successful. Crystallization is difficult, 3D crystallization of membrane proteins, but once you have crystals, the rest is usually straightforward and very fast. And if you want to see the structure of your membrane protein fast, I would always recommend to go for X-ray crystallography, possibly in combination with electron crystallography. If you have specific questions about your membrane protein, or if you tried hard to grow 3D crystals and failed, then electron crystallography is interesting. Or if you want to see your membrane protein in a lipid membrane and want to look at different conformations in a lipid membrane, then electron crystallography is interesting. And in order to be a discussion partner next to X-ray, we need to be fast, and this is what 2DX tries to accomplish, that you can go fast from your data set to your structure. And so we think we should be now in this scheme here, where 2D crystallization with good purification should be possible in 6 months. Sample preparation is still difficult. Somehow you have to find out for each new crystal what kind of preparation is best. Processing and data collection should go hand in hand and should be possible to do in 3 months if everything works fine. We will see that. And then model building depends on the resolution. Yeah? If you have very high resolution, then model building is easy. If you have low resolution, then it takes longer. And the better the microscopes get and the better the software gets for image processing, the faster the model building should also be. The missing cone, obviously, is a source of problems. Of 2D crystals, we can record images in the electron microscope, and the Fourier transformation of an image gives you amplitudes, like in X-ray crystallography, and also phases. You get them directly. And this is what we will speak about in this workshop. You can also use the electron microscope to record diffraction pattern. And then the microscope does not limit your resolution. So once your crystals diffract, any cheap electron microscope will give you very high resolution diffraction patterns. You don't need a high-end machine for that, but you need perfect crystals that are really well ordered and diffract well. And then electron diffraction can be done, as was successfully done with aquaporins, for example. Tom Walz's lab used electron diffraction on water channel membrane proteins and got to 1.6 angstrom resolution. Ruben Diaz used electron diffraction on TMV viruses that were aligned, and he got 0.5 angstrom resolution diffraction pattern. And 0.5 angstrom of a biological protein is TMV. But then you don't have phases. So to get to phases is still a problem. Plus you have a missing cone, plus you need to somehow find lattice lines. So the data processing here is a bit more abstract. Tom Walz's lab uses mostly X-ray diffraction software for that. and is very successful. That's electron diffraction. We will not speak about electron diffraction in this workshop, but focus on images. This here is a crystal that is frozen, and what you can do with images. And the basic idea is you have your crystals that are on a carbon film. The carbon film should be as flat as possible, not too wavy. And you take pictures from the top and also from differently tilted crystals, each time a new crystal. You assume your pictures are a direct projection of your flat crystal, and then you process one picture into one unit cell, and then you combine the unit cells into a 3D reconstruction. That's the idea. This was invented by Richard Henderson and implemented in his MRC programs, and the MRC programs are in Fortran and complicated. We will speak a lot in this week about an algorithm, how individual MRC programs are used to take your raw image and calculate a Fourier transformation and do lots of steps with it, each time using one MRC program. And in 2DX we have hidden all this behind a graphical user interface where you press the go button and the whole thing goes automatically. But in this workshop we still will look at each individual step. And in the end you get a two-dimensional or three-dimensional reconstruction. So this workshop has been set up mostly by Marcel and Sebastian with the help of Karin Bergmann. And Sebastian, do you want to introduce this here? What the program is? Or Marcel, yeah. So.
A warm welcome from my side as well. I'm not Sebastian, I'm Marcel. I'm the main developer of 2DX and will be holding a lot of the practicals. We'll just talk about, I'll talk about the program, what we'll be doing this week. So, as you see, today is mainly going to be introduction, so we're going to show you exactly like Henning already talked about 2D crystallization. Brianka is going to be talking about how you get to 2D crystals. Then Philipp Ringler is going to be talking about how cryo-EM is done. And then we get to a bit more abstract and theoretical part about Fourier, the Fourier transform and Fourier theory. And so how it's organized is that always in the morning we have lectures here, and then the gray parts are the practicals, which will be held in Cherry, which is a computer room, and it's right just 2 rooms further back. So our radius is not going to be that long the whole week. And I won't go into details on the practical right now. It's usually we have tried to schedule it this way that the theory that you get in the morning is going to be implemented or in the practical. So you'll get a hands-on feeling of the theory, and that's how we try to improve your knowledge about it. So the second day is then going to be about just single image processing, non-tilted sample, and we are gonna hear about this contrast transfer function from Henning. I'll be talking about unbending. Then we're gonna hear about synthetic unbending, which is an advanced form of unbending, and from Hans Herberg we're gonna hear about symmetry. Same again, we're gonna have practicals on these subjects as well. On Wednesday then we'll have also again single image processing, but of tilted sample. As Henning has explained, we need projections of tilted sample to get to a 3D reconstruction. That's actually our goal, right? So we're here about the theory here, and then on Thursday we'll go into 3D and how we get to a 3D reconstruction. Same again, we'll hear, we will try to get a 3D reconstruct, or we will 3D reconstruct in the practicals. And then on Friday, We will hear how we evaluate the data, how we can refine our 3D reconstruction with beam tilt refinement. Angie Cheng is going to talk about that, and quality evaluation. I'm really interested in that talk. And then we're also going to hear about something totally different, or not totally different, but we're going to hear about the new software on subtomogram averaging, on tomography, electron tomography. Then on Friday, we all would like to join us to have a tour during our lab, because we're actually not on site. Our group is in a different part of Basel. You've probably seen that on a handout or when you try to travel here. And we would all like you to join our tour during the lab. And for organizational reasons, Sebastian, did you want to talk about this? Are there any questions on the program right now? Good.
Well, that's a warm welcome from my side. Everything I will talk about now you can basically read in the handout you got in your welcome package. I will summarize some important key facts. Well, first, you all have network access here. You can check your emails. You have to connect to the Unibus event account, and the login information then you will find in the manual. It should work basically on the cell phones. We tested it yesterday. It worked on mine at least. Brilliant. And the coffee break, after the first lecture in the morning, we will have a coffee break. And this break is directly outside the lecture hall. And you're not allowed to eat here inside, but you're allowed to drink water from a bottle. You cannot take cups inside, but you can take water in a bottle inside. The lunch will be at the Mensa of the University Hospital. You probably saw the building when you came here, but we will guide you there this lunch today. And there's one important thing, in your welcome package you find 5 vouchers. They are valid for the lunch, and you can take a lunch and a coffee with it. And that's also the reason why all internal participants get these vouchers. No voucher, no food. That's basically the message there. The dinner will be in the first floor of this building on the gallery you probably saw. And there you don't need a voucher because this is our dinner. And we also got a USB key in the package. There you will find all the software and test data set. You can keep this key. You can take the data with you at home. The idea is that we set up everything for you. You can just take it with you and you can start processing your own data on your machine in your lab on the next Monday. The posters, we will not have one particular poster session, but we will have poster walls next to the area where we have our dinner. So you're invited to put your posters there this afternoon or this evening. And the idea is that during the dinner or after the dinner, before the scientific talk, there will be some time for discussing about what you can read on the poster. The IT thing, well, we have in this computer room, we have machines where you can process your data, but there's also the possibility that you have your own laptop with you. And we will try to help you installing the software on this laptop so that you're ready to process your own images. Well, another thing, the toilets, if you want to go to the toilets, just go out, turn left, and it's hard to miss then the toilets. Yeah. You also have our emergency numbers here, and in case you have an emergency or you're lost in Basel or whatever, don't hesitate to call us. We will try to get you out wherever you are. Yeah, and after the scientific talk in the evening, the idea is that you mainly leave the building then because the light switches off at 9:30. Well, I think the talk will be finished at 9, more or less. So after the talk, you're pleased to leave the building. And another catering detail is that, there will not be the possibility to get food and drinks after 8 p.m. So you just have to get whatever you want, and because the external caterer will leave at 8 p.m. So you have to plan a bit that you don't die from whatever. So are there some organization questions right now, or did I miss something? Probably.
No, but I missed something. Yeah, as Sebastian mentioned, we are going to have scientific talks in the evening after dinner. Again here, so I'm sorry for that. So it's going to be from 8 till 9.
Thanks. I pass over to Henning to introduce this group.
Okay, thanks. So, our first presentation is then from Priyanka Abhirafne. She has a long CV and was working on membrane proteins in Toronto, right? And then in Tom Balz's lab, and then in Boston, now here.